So here we are in lecture 3.3. We're continuing our exploration of computational Boolean algebra and binary decision diagrams. Up till now, we've shown you how you make a BDD for a Boolean function, but honestly, in the real world, who wants to manipulate one Boolean output, right? A block of logic on a real chip has lots and lots of inputs and lots of outputs. We need to be able to manipulate lots of Boolean equations at the same time. It turns out that BDDs naturally support that. In fact, we can share nodes in BDDs so that many different functions can be using the same ecosystem of nodes in the BDD, and it turns out that one actually gets more efficient BDDs. So in this lecture, we're going to show you some examples of how sharing actually enables us to represent complicated sets of functions with one set of BDD nodes.
So now that we know how you build a reduced ordered BDD by starting with a decision diagram, at least conceptually, requiring a total variable ordering from the root to a leaf, and then reducing the BDD so that there are no redundancies so that you get the smallest, tightest possible BDD, let's just talk a little bit about the interesting things you can do. So the first thing is that you can represent any function, any Boolean function of anything as a reduced ordered BDD, and you can do so in a canonical way. So some lovely things happen. What if I told you that my function of variables x1 through xn is a 0, right? How might we represent that as a reduced ordered BDD? Well, really, there is only one option. There's exactly one option, and it is that. If this function is equal to 0 for all possible inputs, then it has to just be a pointer to the 0 node. What if the Boolean function is a 1? All right, well, then the same thing is going to happen. If the Boolean function is a 1, then it has to be a pointer to just the 1 node. And I'm going to go off to the side with this little text box here and say, let's just remember something. In a reduced ordered BDD, a Boolean function is really just a pointer to the root node of a canonical graph data structure. So you point to the top node of the BDD, and then you descend the BDD, and that's how you determine the values of the function for the variables of interest. If f is a 0, it's a pointer to the 0 node. Period. There's no other way of that happening. And if the function is a 1, it's a pointer to the 1 node. There's no other way of doing it because reduced ordered BDDs are canonical. There is one and only one way to represent every function. So that's just a very nice, simple thing. What if, in contrast, the function is of variables x1, x2, ... xn, and we just pick one of those variables. We just call it x. And we say that that function is just x, and we ignore all the other variables. Well, then we're going to get a variable node, and the low child is going to point to a 0, and the high child is going to point to a 1, and the function itself is going to point to that x node. So it's a really very nice, simple kind of a thing. What if we have a more interesting function, a function that's actually got a little bit of complexity to it? Let us assume that we have a function and that it's a function of 4 variables, x1, x2, x3, and x4, and that the ordering is in fact x1, x2, x3, and x4 in that order. So here's just a simple function on the left, x1 plus x2 and x4. What we'll notice is that, interestingly enough, there's no vertex labeled x3. It would be in here somewhere if it existed, because it has to be after x2 and before x4. But this particular function does not depend on x3, and so there are no x3s. And lots of graphs are shared. We're going to talk about that more extensively in this talk. This particular function is really just, again, a pointer to the top node on this BDD, because a BDD is really just a pointer to the variable that defines the top of the BDD graph data structure. And you can see, if you just think about this for a little bit, that this BDD actually makes sense. For example, this thing is really x1, x4 plus x2, x4. And so what I expect is the only two ways to make this function a 1, okay, are I need to make the first term a 1, or I need to make the second term a 1, right? And the way to make the first term a 1 is to go down this path, which says x1 has to be a 1 and x4 has to be a 1. And the way to make the second path a 1 is to go down this path, which insists that x2 is a 1 and x4 is a 1. So it actually works. Odd parity is a more interesting, kind of a denser, if you will, a more compact function. Odd parity is x1 exclusive or x2 exclusive or x3 exclusive or x4. And it's odd parity, which means that it makes a 1 if and only if there is an odd number of 1s among the inputs. So, for example, if we just think about, let's say, x1, x2, x3, x4, imagine we have 1, 1, 1, 0. Let's see if this works. Okay, here's x1 is a 1, here's x2 is a 1, here's x3 is a 1, here's x4 is a 0. Yeah, it makes a 1. Right, so this is this sort of zigzag sort of path back and forth. This is a very dense way of capturing the fact that I only care about when an odd number of the representative variables take the value 1. That's the only way I can get to a 1. Any path with an even number of zigzags takes me to a 0. It's a very tight representation. It's a very kind of elegant and compact representation. And it is also illustrating another very important technical point, and that's sort of the substantial point of this particular lecture. Every BDD node, not just the root, but every BDD node represents some Boolean function in a canonical way. Now, you might create the BDD on the left because you choose to want to manipulate x1 plus x2 and x4, and that's great. But every node inside the BDD is the root of some subgraph, and every single one of those represents some other function, even if you didn't want it, even if you didn't try to create it, it just happens. Right? So for example, this, right, is f, and this is f. Right, x1 plus x2 plus x times x4. That's great. What if I tell you that that function is a g? What is that? Right, and the answer is, if you kind of stare at it for a little bit, that g is equal to x2, x4, and that makes really good sense. The only way to be able to get to the 1 node from starting from g is x2 is a 1 and x4 is a 1, so g is x2, x4. That's just that's just an AND gate with x2 and x4 as its inputs. If we look at the BDD on the right, okay, and we say, all right, now this is f, right? So f is equal to x1 exclusive or x2 exclusive or x3 exclusive or x4, and now I start pointing at intermediate nodes like that node. What do I get? Well, if you stare at that one, that node is actually the root of the function x3 exclusive or x4. Right? The only way you can get to the 1 node is if x3 disagrees with x4, if they have different values. And conversely, the one on this side, right, the one on the right-hand side of the exclusive or BDD, is x3 exclusive nor x4. And just by way of reminder, that's just an exclusive OR gate with a inverter bubble on the output of it. And that's actually the even parity function for 2 inputs. And similarly, the one on the right-hand side here, the x4 node, that's actually just the root of the function x4 bar, right? And you stare at it and you say, oh yeah, if x4 is a 0, I get a 1. And if x4 is a 1, I get a 0. Okay, that must be not x4. Now, we can take this idea that every node inside a BDD represents a function, and we can take this to sort of the next logical step, which is that we can do something useful with this fact. So here's a more interesting, rather more realistic example. So let us consider a 4-bit adder. And so the yellow box that I'm showing you on the left-hand side is a 4-bit adder. It has 2 sets of 4-bit numbers as its input. It has A3, A2, A1, A0, that's a 4-bit number, and it has B3, B2, B1, B0, it's another 4-bit number. It adds those numbers together. It produces a sum, S3, S2, S1, S0, but I don't care about anything other than the most significant bit, the high order bit of the sum, that's S3. And it's got to carry out. And I will note here, just for completeness, that there is no carry in this example. All right, so there's only a carry out, and there's a high order sum bit. If I were to build the BDD for the sum bit, S3, that is the BDD shown on the left. It's got a lot of exclusive OR kind of structure because, things on the inside of adders are lots of exclusive OR kinds of things. And it's got a positive logic carry chain that tells you when the carry wants to be a 1, and it's got a negative logic carry chain that tells you when the carry into the high order bit wants to be a 0, and then you can decide, based on those two things, with a little bit of XOR computation at the top, whether the sum 3 bit is a 1 or a 0. If you then go look on the right-hand side at the other BDD for the carry out, you see it's got really quite a lot of the same structure. And in fact, the big gray box, which is what I am highlighting, so I'm just going to sort of outline it here. There's this big gray BDD over here, and then there's this big gray BDD over here. Those things are basically the same shared subfunction, and I can say that even more strongly. Those things are identical graphs. There is nothing different. Those things are exactly the same. And so we get an interesting question, which is, in any realistic kind of a digital design scenario, you don't build a BDD for one function. You build a BDD for a whole lot of functions. Maybe hundreds and hundreds of functions. So, it's not at all unreasonable that I'd like to build the BDD for the sum 3 bit, and I'd like to build the BDD for the carry out bit. Do I actually have to build all the stuff in gray twice? If I physically build a BDD package, and I physically build the data structures for the sum 3 bit and the carry out bit, do I have to physically build 2 copies of those gray nodes? Gosh, I hope not. That would be very, very inefficient. And it turns out that there is really good news. One doesn't have to represent it twice. One can have the BDD have multiple entry points or multiple roots, right? One can simply share that subgraph. And so as I'm showing it here, again in gray, right, the carry out function gets to use it. I'm going to circle the parts of the carry out function that use it. And in addition, the sum 3 function gets to use it. And the way it gets to use it, right, is that there's this shared BDD subfunction, and the carry out gets to send some edges pointing to it to use it, and the sum 3 gets to send some edges into it, getting to use it, and you just share it. Right? And so these things are called multi-rooted, which just means that there's more than one pointer pointing to the node. There's a single node up there at the top that defines the entry point of the BDD. So these things are called multi-rooted BDDs. And again, every node in a BDD represents some Boolean function. So this multi-rooting idea is just explicitly exploiting all of this to better share stuff. So it turns out it's sort of an engineering idea, but it's a wonderful and simple idea, and it actually makes things very efficient. Ah, you ask, how efficient? Oh, it makes things wonderfully, magnificently efficient. And so here's a lovely example from Randy Bryant again. Why stop at 2 roots, right? Why not have as many roots as you want, right? So if I have a, sort of a shared subfunction here, I can have all kinds of people wanting to use that thing, as many as I like. So these are big savings for sets of functions. You can minimize the size over several separate BDDs by maximizing this sharing. So the thing that I'm actually showing you on the right is the full 4-bit adder, right? So this is the full 4-bit adder, right? And so what you're seeing are the 4 sum bits, okay, and also the carry out. So eight things go in, 4 A's and 4 B's, as you can see here, A0 through 3 and B0 through 3. And 4 things come out, 4 sum bits, and 1 carry out comes out. Now, how much savings do you actually get when you do stuff like this? Well, if you were to build the BDDs separately for each of the bits of the sum and the carry out, if you had a 4-bit adder, it would be 51 nodes, and it would be almost, 12,500 nodes for the 64-bit adder. But if you shared them, it's 31 nodes for the 4-bit adder and 571 nodes for the 64-bit adder. Now look, the difference between 51 nodes and 31 nodes is no big deal. The difference between 12,000 nodes and 600 nodes is a factor of what, 20? That's a gigantic savings, and it just gets bigger as things get bigger. So the multi-rooted idea, the sharing idea, the fact that we can exploit the fact that every node in a BDD is a Boolean function, and if somebody else needs to use it, they can just point to it. That's a wonderful thing. That's just a really great, great thing about binary decision diagrams. And so this lecture has been all about the fact that BDDs are shared data structures, that we can build lots of Boolean functions in the same data structure, that every node in a BDD represents a Boolean function, and that we can reuse those things in appropriate ways with multi-rooted graphs to do really significant amounts of engineering savings. So next, what we want to talk a little bit about is how people actually implement these things.